Ladies, this is Mrs. Blaufuss, and this is the next lesson. It's the lesson after 3.3, and it's about linear programming, but it ties into graphing linear inequalities, and then also picking a solution. So it's kind of a combination of a few different things that we've already done so far, but you have a few key terms, and so pause the video as you jot down these key terms, and then we'll start with some examples that are on your assignment guide, or on your notes sheet rather. But optimization is the best solution. So for whatever you're looking for, what's the best possible solution for that? If you're looking to optimize profits, or maybe you're looking to minimize costs, optimization is whatever your best solution. It is related to your objective function, whatever your objective for this program is. Linear programming is maximizing or minimizing the objective equation while you're following constraints. So your constraints, we'll jump down to that one, are linear inequalities that are used to express any of the given information. And then your objective function is a linear equality. So constraints are inequalities, but a function is a linear equality. And this linear equality has two variables. And those variables are going to be the same variables you use in your constraints. You're going to constrain those two variables somehow, or at least one of the two variables. And then lastly, your feasible region. This is what we formally refer to as our solutions. But this feasible region is the intersection of our graphs. So all of our constraints, where those constraints intersect. They will all intersect in linear programming. They will all intersect in some region. You won't have a no solution for those constraints, because then you wouldn't be able to exercise any of those options, because they wouldn't follow all of the constraints. So your feasible region is the intersection of all of your graphs. This first example related to the potter and making bowls and plates, we're going to skip that for now because it's a little bit longer, and I want to get familiar with the constraints and objective function before we go into that. But on your guided note sheet, you see this key concept, feasible region, and you either have a bounded feasible region or an unbounded feasible region. If it's bounded, like this first graph here, that means you have a polygon. So in this case, it's a quadrilateral, but it could be any. It could be a triangle, it could be an octagon. But you have this polygon that is where the region is confined within this polygon. So in a bounded region, you have both a minimum and a maximum related to your objective function. And with an unbounded feasible region, you have either a minimum or a maximum. So not both. A minimum or a maximum. And that minimum or maximum still will occur at these vertex points, just like the minimum and maximum will occur at one of the vertices. But with an unbounded region, you don't have both a minimum and a maximum. Okay, so looking at the next example, example 1, first of all, on your coordinate grid that you see on your note sheet, make that into a coordinate plane where you actually have 4 quadrants. You need 4 quadrants because you deal with negative numbers in your constraints. So here, y has to be greater than or equal to -1. So that's how you know that you need extra quadrants. But sometimes we'll just work in the 1 quadrant, but in this case we need 4. So this one asks us to find the minimum and maximum value of the objective function, which they give us. This objective function, c equals 2y plus 3x. But before we use this objective function, we have to actually graph our constraints. So we're going to graph our constraints and shade in the solution of those constraints. So let's start with x is less than or equal to 2. So here is where x is 2. Now our solution for this is going to be anything to the left of that. So here's my solution for the first constraint, my possible scenarios for the first constraint. Now I have to do my second one, y is greater than or equal to -1. So I'm going to graph that. And I'm going to graph my solution, which is anything above where y is greater than, or where y equals -1, anything larger than that. And then my last one, y minus x is less than or equal to 3. I'm going to plot this. It looks like it's in standard form, so I'm going to use my x and y intercept. So if my x is 0, my y is 3. So make sure that when you do this, you're actually working on the x and y axes and not on those horizontal and vertical lines that we just graphed as part of our constraints. And then my x-intercept is when y is 0, so negative x is less than or equal to 3. So that means x is less than or equal to -3. Okay, and then I'm gonna make my line with those points. And then I can pick this any point that's not on my line to see whether or not it's a solution. So 0, 0. So 0 is less than 3. So my solution for this one is below the line. And I'm looking for any place where all 3 of these intersect. So my feasible region, and I'll just highlight it for you in a different color so that you can see it a little bit easier. I'll use, I'll just use gray. It'll be easier to see. But it goes anywhere from here to here and down here. So my feasible region looks like a triangle. And my next step now is to identify the vertices. Because if you, again, look at that for your notebook, key concept thing, it says that the maximum and minimum value occur at each vertex of the feasible region. So I need to identify my vertices of my feasible region. So this point here is 2, -1. This is 2, 5. And this is -4, -1. Okay, so those are my 3 points, and I'll jot them down here too. And now I'm going to use these, and I'm going to plug those values into my objective function to see what my maximum value is and what my minimum value is, and which of those points output those values. So C equals 2y plus 3x, that's my objective function. So C equals 2 times y, which in this case is -1, plus 3 times x, which is -4. 2 times -1 is -2, plus 3 times -4 is -12. So -2 minus 12 is -14. Now, I don't know if that's my minimum or my maximum or somewhere in between until I do all 3 vertices. So the next one, C equals 2 times y plus 3 times x. And that equals 10 plus 6, which is 16. And then lastly, C equals 2 times y plus 3 times x, which is 4. So if think about your number line, which one is furthest to the left? That's your minimum. The one furthest to the right is your maximum. Okay, so this first one, this is my minimum, and the second one is my maximum. So I'm going to write this as my minimum is this point, -4, -1, and that gives me -14. Now, sometimes it might ask you for the actual value, but in this case, it just asks for the minimum and maximum. So we're looking for a minimum x value and our minimum point and our maximum point based on our objective function. And then our maximum is 0.25, which gives us 16. Now, you can't just look at your graph. Just looking at your graph and trying to identify a minimum and maximum is not going to work because it depends on what your objective function is. So if our objective function was something completely different, like, for example, c equals -2y minus 3x, we would get completely different minimum and maximums. Our graph would still look the same, our feasible region is still the same, but we can't just look at our graph to identify our minimum and maximum. We need to actually plug in those values into our objective function. Try the next example on your own. Please pause the video while you work, and then you can unpause and I'll go through the solution. All right, here is our next example, example 2 on your note sheet. And we're looking for the minimum and maximum value. And our objective function is c equals x minus 2y. So you should have graphed the 3 constraints where x is greater than or equal to 1. And with this example, you can use 0, 0 as the intersection of the x and y axes right down here. And we're really only working in the first quadrant of the coordinate plane because we don't have any negative numbers. But we need to still graph x is greater than or equal to 1, and that's the purple line that you see. The second one, y is greater than or equal to x plus 1. So that's a y-intercept of 1 and a slope of 1. So that is the green line that you see. And then the last one, y is less than or equal to 7 minus x. If you rewrote this into slope-intercept form, you would have y is less than or equal to -x plus 7. So we have a y-intercept of 7 and a slope of -x, and that's the orange line that you see. The feasible region is that blue region. You should have shaded that blue region in. And then identify the vertices. So the vertices, 1, 2 is 1 point, 3, 4 is your second point, and 1, 6 is your third point. And then if you plugged in those values to your objective function, where x is 1 and y is 2, you got an output of -3. If you plugged in 1 and 6, that coordinate, into your objective function, you got an output of -11, which turns out to be your minimum. And then if you did the last one, which I don't have up here, but if you input 3 as the x value and 4 as the y value, you would have got an output c equals -5, which that's right in between -3 and -11, so we don't really care about it. It's not the minimum and it's not the maximum. So we don't even need to mention that in our answer. All right, and then if you feel confident, you can work on this next example on your own, but I will walk through it if you want one more problem review, and then we'll go to the story problem. So if you want to jump right to the story problem, just skip this. It's example 3 is we're finding the maximum and the minimum value of this projective function where c equals y plus 2x, and we have these constraints. X is greater than or equal to 0, and y is greater than or equal to 0. I'm going to graph those right away because they're just like my x and my y axes. So again, this is basically just saying that I'm working in this quadrant. So I'm not going to shade in this because this is the only quadrant that I'm going to be working with. Okay, and the next step is to graph my next 2 constraints, and the first one is in standard form. So if y is 0, then my x is 8/3. So let's see. I'm going to go, well, let's see what I'm going to figure out my y-intercept first before I decide what kind of scale I'm going to use, because I might use like each one of these is 1/3. So where this is 1. But let's look and see what the next intercept is. So my y is 8 divided by 2 if x is 0, which is 4. Which doesn't look like I have quite enough room to use 3 for a block, so I'll just use 1. Scale of 1 to 1. Okay, and then, so I can graph this. Actually, you know what? I am going to use 3. So this is 1, and then I'll just use 1s for my y. Maybe I'll use 2s. So you can use different scales. It doesn't really matter as long as you're consistent along the x-axis and consistent along the y-axis. Okay, so I'm going to do 8/3, which is right here. And I'm going to do 4, which is right here. And then I'm going to graph that line. Okay, and then 0 is not greater than or equal to 8. So my solution for this is above the line. Okay, and then my next one is 3y plus x is greater than or equal to 5. So I'm going to do my x-intercept first. So if my x is 0, or if my y is 0, my x is 5. So I'm going to go ahead and plot that point here. And then when my x is 0, my y is 5/3. So let's do x is 5, y is 5/3. So I could have gone up by thirds, I guess, with this one too, but we will just estimate as best we can. So 5/3, which my graph is going to be a little bit off. Okay, well, all right, I had to fix my scale because I had started with 1 here, which that doesn't work, so that was inconsistent. So if you need to fix your scale, please do that. So I changed my scale on the y-axis so that each unit is actually a third. So it takes 3 units to get up to 1. Okay, so my y-intercept is 5/3. So I'm going to plot that point here. And I'm going to use my x and my y-intercepts. And again, I'm going to pick 0, 0. 0 is not greater than or equal to 5. So I need to shade my solution above. So it's above this line. Okay, so now you can see that I have a lower boundary on my graph, but up here, all of this area up here, there's no boundary. Okay, so I don't have a bounded feasible region. I have an unbounded feasible region, but I can still take these 3 vertices that are on my boundary to see if I have a minimum or a maximum value. So I'm going to still take those points. This is 0, 4. This is 2, 1. And this is 5, 0. Still going to use those, and I'm going to plug it back into my objective function, where c equals y plus 2x. So c equals 4, looking at my first point here, 4 plus 2 times 0, which equals 4. C equals y, which is 1, using this point, 2, 1, plus 2 times 2, which is 5. And then C equals y, which is using 0.50 now, y plus 2x, oops, x, which is 5, which equals 10. Since this one is an unbounded region, we have a minimum here, but there is no maximum. So in this example, again, it's unbounded. So we have a feasible region, but unbounded feasible region. So in this example, we do not have a maximum. We have this minimum at 0, 4. But we don't have a maximum. Okay, so we're going to rewind and go back to that first example, that story problem, because some of your homework problems have word problems where you have to actually set the constraints. So take a minute just to read through this, pause the video while you read it if you need to. But the question is, and this is the question that we're going to answer, to identify our x and our y variables, and also the question that we're going to answer for our optimization function, or our objective function, rather. So this last question is, how many bowls and plates should we make? Okay, this tells us that we're looking for a number of bowls and a number of plates. So we're going to use our x value as a number of bowls. Number of bowls. And our y value is number of plates. Okay, now the second part is that he's wondering how much he has to make of each in order to maximize profits. So that tells us that our objective equation deals with money. So you can write your constraints first, or you can write your objective function first. Since we're talking about it now, let's just write our objective function. So how do we maximize profits? We're dealing with our variables x and y, where x is the number of plates and or x is the number of bowls and y is the number of plates. And we know that a profit of a bowl is $35. Profit of a plate is $30. So our objective function is our total profit equals $35 for every bowl, which is our X value, plus $30 for every plate, which is our Y value. Okay, so we've got our X and our Y variables defined. We've got our objective function. Now we need to identify our constraints. So first, let's write a constraint related to number of bowls. It says that we need to make at least 4 bowls. So that means X has to be greater than or equal to 4. Now what about Y? Do we have a specific number of plates we have to make? It doesn't specify, but we can't make negative plates. We can't make -5 plates or -10 plates. So our Y has to be greater than or equal to 0. So if you can't have a negative of one of your variables, then you have to say that. You have to say that Y is greater than or equal to 0 to indicate that it cannot be negative. Okay, so next, for the last piece of information that it gives us is that we have 40 pounds of clay. So the number of bowls that we make and the number of plates that we make has to use combined less than 40 pounds of clay. So an objective equation a constraint for this information is we know that a plate uses 4 pounds and a bowl uses 5 pounds. So 5 pounds for every bowl plus 4 pounds for every plate has to be less than or equal to 40. Now we have to actually graph these constraints so that we can look at our feasible region. So I'm going to graph the Y is greater than or equal to 4 first. And then X is greater than or equal to 4, and then Y is greater than or equal to 0. And then I'm going to use my intercepts to graph the 5x plus 4y is less than or equal to 40. So when x is 0, y is 10. And then when y is 0, x is 8. So here is my feasible region. Okay, now I have to actually identify it because I didn't do any shading as I went through this, and I should have. But x is greater than or equal to 4. So that's this area for my first constraint. Y is greater than or equal to 0. I'm not actually going to shade that because it would be this whole part here. So then I'm just going to do my second one, and I'm going to use 0, 0 for my x and y. 0 is less than 40, so I'm going to shade below this line. And my feasible region is where those graphs intersect. So I've got this point, and this point. Now I'm going to actually identify those points as 4, 0, 8, 0, and 4, 5. Now I'm going to take these x and y values, and I'm going to plug them into my objective function. So I'll start 4, 5, 4, 0, and 8, 0. So my profit is 35 times x plus 30 times y. And if I help that out, I get $290. My second one, 35 times 4 plus 30 times 0. And if I help that out, I get $140. And then last one, 80, 35 times 8, which is my x, plus 30 times y. I get $280. So how many bowls do I make and how many plates do I make in order to optimize, in order to get my optimization, my best possible solution? This first one here gives me $290. That's my best solution. It's just a little bit better than my $280 solution. So just with this given information, I would want to make, I would want to make, or the potter would want to make 4 bowls and 5 plates. To earn profit of $290. Alright, so I know this video is kind of a longer one, but we did go through most of this in class, and you may just want to review this word problem, which I'll post the time on Moodle, and maybe review the unbounded usable region. So just reference this video anytime for extra practice, and please come see me or ask questions during class next time I see you if you have any. Thanks, girls.